This is the posted homework for you to practice using Euler's method. So you need to find the approximation to the integral curves of the following system. This is the system, and the solution curve you're trying to approximate is this solution curve, which is vector valued. And then this curve's derivative is equal to the right-hand side. That is our vector field is depending on the component of this vector, this x vector. So you see, so it's autonomous. And we recall that Euler's method is applicable to equation of this form. So let's write that is the derivative equals some function, right? The expression. So we can use f. This can be a time dependent or a time independent. So, but this right-hand side is denoted by this f, which might depend on t and y. Okay, so this is the form, and we realize this given problem, the given problem is just that form. Suppose I name this vector as x. This vector has two components. So I say this derivative of this vector is equal to the right-hand side. You see, our right-hand side, this vector field, which is equal to derivative of x vector. This is what we denoted, right? Denoted by capital X. In this example, it doesn't depend on t, so you can just write it depends on the x vector only, the lowercase x. So immediately we see, so the format for a single equation, for example, or a system like this, they're the same form. If we have the Euler's formula for this single equation, let's apply it to this system of two differential equation case. So let's apply it to this one. So recall that Euler's method for the single equation, it is for the next y value, it is the yi plus h, the function at the previous time, and yi. H is the step size. So for the current problem, our notation for y is the x vector. So let's say x vector, and notation for the solution at the next time is denoted by with the superscript I plus 1. So I just write it as this form. So the right-hand side, this we denoted by capital X. Evaluated at x sub I. So this is our Euler's method. See exactly the same format, right? The previous plus the h times the slope function. Here, slope function is replaced by the capital X. So use that format, you will calculate the X. So here we set up the notation, just so you know what is the meaning of X superscript. The reason is a lowercase x. So this is our, see this part, this is our capital X, which is depending on each component of the X vector, right? X1, X2. So this Euler's method for solving our system of two equations. And just to be aware of the meaning of the notation. So the reason I picked this notation instead of x sub I, it is because x sub 1 and x sub 2 already has a meaning, right? x1, x sub 2, the subscript has a meaning. They denote the first component of the x vector, second component of the x vector. So, so we don't want to create confusion. So that's X itself has two components. So the first one is denoted by X1. The second one is denoted by X2. So we already used subscript. So the X1, X2, of course, each one is a function of t. Although, yeah, we often omit the t. So we keep in mind this is a t, but when we discretize the t, so suppose we start from a certain t, like when t is 0, right? So we can call that starting from t0. And then we go forward. So in the direction of the time, we want to find the solution x, the vector. This is solution x at different times. So that's what we're trying to do. So if we know the solution vector when t is t naught, here t naught is 0. You see this initially t is 0. So at 0, the solution is given. So the solution is given as 1, 1. So we can think that solution vector when at 0, right? So we put the I, that ti correspond to the solution x superscript I. So the explanation for this notation is x sub I is the solution vector evaluated at t sub I. That also means each component of the solution vector at t sub I. So that is this I, means we discretize, you see, from T0 to T1, and T1 to T2, we want to find solution curve or the solution vector at different times, just like Euler's method will provide approximate solution at each T sub I. Okay, so now that explains this process, the notations that we use when we apply Euler's method. So that means you're starting with the initial when I is 0. When I is 0, that is the solution vector when at t 0 initial time. So we're given, actually our problem t0 is 0 and x superscript 0 is the 1, 1. So we have that one already 1, 1. So that vector is given. And then at t1, what's the solution vector by this method? So you just use Euler's method. You see, from x0, you can possibly get x superscript 1. So you will get a new vector at x1. And once the x1 is found, you can find x2. So here from x, another vector which is denoted by x superscript 1 at t1. So then at the solution vector at t2, the solution vector at t3. So that's our notation. So it's very easy to apply Euler's method, and even if you do it manually, you see this each step is straightforward, and just try to understand this method and how it can be used to vector valued solutions. So once you find the x as a vector, then you can draw that vector, because this each component, right, at ti is known. Okay, first and second component at a certain time given. So when at different t's, you can plot the component function for different t's. Yeah, so we can do it this way. Just the ti. So you can plot t and the x. So just like any function. So if you want to put the t here, so each ti and the component x1 will be a solution curve. So you can draw a curve for just x, the first component of that vector. Right? Because we find already at different t values the first component. But same thing. So for each time, you can also draw the second component. So first component at different t's. So it's just approximation to the first component of the exact solution. And the second component can be done similarly. That is, if we from T0, T1, T2, etc. So you can get approximate second component. So the second component of x versus t can be shown. So suppose the second component, you found it, then the component as a function of t can be approximated by this numerical solution. So we have given this, but this question, you don't have to give each component as a function of t. Actually, you just simply put x1, x2. So instead of doing this, we will put x1 versus x2 at different times. So ti, for each specified ti, we have this pair. So we want to see the trajectory of the integral curve x. So in R2, that is this x, in the two-dimensional space, you just show x1 versus x2. And then at each starting from t0, which is given, right? That's 1, 1. You have 1 point in R2. So start from that point, you calculate when I is 2, that's another point. So each ti will give you an ordered pair in R2. So the goal of this exercise is just for you to show these ordered pairs, like you did a scatter plot for each ti and produce a point, right? That's x1, x2, a point. So this point with corresponding to each ti, you see, start from t0, start from this 1, 1 point. So see what is the shape, how it develops. That's the integral curve in R2. Yeah, you will notice the approximating polygon. For this initial value problem, you see we have not only a governing equation, but also a given initial value. So it is actually an initial value problem, and you try to show the trajectory. I mean, the integral curve for this problem. That is your approximate solution to this problem.